Hi everyone, I'm Andres, and this is a joint work with Paul Skripczyk, where we have basically derived a four-way correspondence between quantum horse betting, dependence measures, Rényi divergences, and resource monotones. Right, this is the outline. First, I'm going to start with the framework of quantum resource theories. Then I will move on to the motivation and the specific questions that we wanted to solve. Then we will be answering these questions and finally, well, some conclusions and perspectives. Right, so starting with the framework of quantum resource theories, one usually starts by defining the objects of the theory. In this case, we're interested in measurements, which, as we know, they are a set of operators such that they are positive semi-definite and they add up to the identity. Then one defines the resource or the property of these objects that we want to think of as a resource. In this particular case, we're going to be addressing informativeness, which is basically, and therefore we define the set of free measurements as or resource-less measurements as the measurements that do not have the property, and therefore we call them here uninformative. And an uninformative measurement is a measurement such that the POVM effects can be written as being proportional to the identity. Here in this diagram we have that informativeness in particular forms a free set of measurements that is convex. And here, for instance, this point is just an example of a resourceful measurement, in this case, an informative measurement. Of course, within the framework of quantum resource theories, there are items which are of interest and subject of research, like resource quantifiers, operational tasks, free operations, and many others. I'll refer you to this interesting review from last year on quantum resource theories for more information. Right, moving on to the motivation and somehow the specific questions that we wanted to solve. Here we have some results from last year and this year, which is basically a three-way correspondence between operational tasks, resource quantifiers, and dependence measures or information theoretic related measures. So for instance, the first one, which was first derived, is the one in black, which states that from the side of operational tasks, we have, for instance, quantum state discrimination is connected to the quantifier of generalized robustness, and they are also connected to the quantity called the accessible information. In parallel to this work, it was also derived that there is a second correspondence now linking quantum state exclusion to the quantifier of weight of informativeness in this case, and to the excludable information. And well, these corners are related by means of these equations that we have here. In other words, it's basically saying that these specific resource quantifiers are somehow characterizing these operational tasks, and similarly for these information theoretic measures. Now, before we get into the main question that we want to solve, let me allow us to cut here, to cut this side here, and then we can introduce a fourth ingredient in terms of Rényi divergences. This is something that it was not explicitly addressed in any of these references, but still it is something that it is nowadays considerably well known. Which was first noted by Data in 2009, which is basically the fact that the quantifier of generalized robustness is connected to the Rényi divergence of order plus infinity, and a similar trick can be done for the weight. And therefore, we're going to introduce here these four ingredients in terms of Rényi divergences. Therefore, we have a diagram like this with here, well, we address the accessible and the excludable information in these more fancy terms, but They're basically the same quantities, and we have also lifted the resource quantifiers to something that is a slightly more general, which is the concept of resource monotones. Right, so having a diagram like this, the first thing that we can identify is that we have some plus infinities here in the outer triangle, and we have some minus infinities on the inner triangle. And therefore, we can think about, well, the outer triangle being somehow like plus infinity, and the inner triangle being, the inner rectangle, sorry, being minus infinity. And therefore, one can wonder whether these two parallel four-way correspondences now are just particular examples of something more general, such that they can be recovered as examples, as particular cases. So this is the main question, whether there is something here in the middle between these two correspondences. And then, well, in order to somehow try to make progress in this direction, well, one needs to be more specific, and therefore, well, we want to fill somehow this space here, which means that we need to find, for instance, we have a first question here, which means that we need to find an operational task somehow that is including discrimination and exclusion, hopefully via a parameter such that when we tend to plus infinity, it recovers discrimination, whilst when it tends to minus infinity, it recovers exclusion, and similarly for the other ingredients. So this is somehow the four specific questions. In this talk, I'll be going through question 1 and question 2, and we will see how they are connected. And in fact, once that is done, one can also derive answers for question 3 and question 4, but unfortunately I won't have time to address those. Right, so let us answer question 1 and question 2 and address how they are related to each other. So question 1 is about an operational task recovering discrimination and exclusion, and it turns out that that comes in the form of quantum horse betting games. Horse betting games, they date back to the work of Kelly, and recently they were also addressed by Bleuler, Lapidus, and Pfister, which we have to say that these two works, everything until now has been within the classical domain, as in within classical information theory. In order to answer our question, we had to extend to the quantum domain these games, and therefore we have called them quantum horse betting games. Now, in terms of question 2, there are a bunch of different dependence measures to take inspiration from, but it turns out that the one that does the job here is the one due to Arimotos, and well, which takes this form, and it is being parameterized by this alpha here, which goes from minus infinity, which can go from minus infinity to plus infinity, and we can think about this as being a generalization of the standard information, the mutual information of classical information theory. Right. Well, Arimoto's dependence measure, basically this function here. So probably the one that deserves more explaining is the operational task of quantum horse betting games. So that is the one that we're going to describe now. So we are calling them quantum horse betting games, but probably a more accurate title will be horse betting games with quantum side information, but still we're going to stick to quantum horse betting games just as a shorthand. Right, so as I was saying earlier, horse betting games, the classical version of them, the standard version, dates back to Kelly and this recent work by Bleuler, Lapidus, and Pfister, and therefore our first job is to extend to the quantum domain this task. So now consider a horse race distributed according to a probability distribution P. So we have K horses here. And then this game involves 3 agents, a bookmaker, an informant, and a gambler. In a first instance, the bookmaker is going to be offering some rewards in terms of this function OX, which is not necessarily a probability mass function or a distribution. And then an informant is somehow which his goal is going to be helping somehow the gambler. Is going to encode the information of the winning horse as a set of states, and therefore this together with the previous uh, probability distribution P, this is going to define an ensemble here, and at some point the informant is going to send one of these states to the gambler, say row X. Now the gambler, who is in possession of certain initial wealth, his goal is going to be proposing a betting strategy in the form of a conditional probability mass function B in order to distribute and bet with all the initial wealth. This G here is going to be the side information that the gambler is going to extract from the measurement that he received from the informant. And he's going to extract that information by using a measurement M. And then, he's going to obtain side information G according to the Born rule. So now, in principle, the gambler is going to be playing with two objects: this conditional probability mass function and the measurement M. Finally, in a particular game that we're going to call horse discrimination, the gambler is going to be rewarded only for the percentage of wealth P of a given G allocated to the horse that ended up winning, in this case X. Right, so that is the game. And now the figure of merit of these games come in the form of the so-called log average wealth. Here, well, we can understand it in this way: log of this W, which is the average wealth, and we can see that this is an average wealth because, well, we are averaging here, and this expression here is going to be the wealth. Remembering that O is the odds and B is the betting strategy, and therefore this whole quantity is the wealth. We're also including parameter beta here, which is going to represent the risk taken by the gambler. And for more information, please look at this recent reference. Now, our main result, which is going to be connecting quantum horse betting games to Arimoto's measure of dependence, is given in the following form. Again, consider a horse race distributed according to P, an informant encoding this information as a set of states row X, and therefore defining an ensemble of states E. Now a bookmaker is going to be offering constant odds, which again is not necessarily a probability mass function, and the gambler is going to be, it's going to have a risk factor parameterized in this way, and it's going to be using a fixed measurement M. So now we want to analyze the following ratio. Here we have in the numerator we have the wealth of obtained by the gambler when playing this particular horse betting game with the fixed measurement, and we're going to allow this player to maximize over all possible betting strategies, the best. And then we want to compare this type of player against a player who is only allowed to use uninformative measurements. Here we're going to be maximizing. We have the same game. We're also going to maximize over betting strategies, but now the measurement we're going to maximize over all free measurements or uninformative measurements. And then we're just going to take the log of that quantity. So this somehow is quantifying the advantage of using measurement M against all free measurements. And then, well, our main result is that it is equal to the Arimoto's measure of dependence. Here, we are playing horse discrimination, and this specifies alpha being greater or equal than 0. And something similar, we can do something similar when playing a variant of horse discrimination, which we call horse exclusion, and that is going to be characterized by Arimoto's measure, but now with negative values of alpha. So that is our main result. And then, therefore, we can now answer this question here and say, well, this operational task is quantum horse betting. And here, well, we have now Arimoto's measure of dependence. From this insight, from this side, from answering question 1 and question 2, we can answer as well question 3 and question 4. Unfortunately, I don't have time to go into those. But then the overall result is that the answer is yes, we can indeed find a more general four-way correspondence such that the examples of plus and minus infinity can be recovered as particular instances. Finally, as perspectives, well, we have done it for something very specific, which is measurements and the resource of informativeness. We want to know whether this is or something similar could hold for additional resources and additional objects like states or channels, as well as probably there could be other ways to connect extremes. And also we're interested in looking at further operational tasks with this concept of risk. With that, I would like to thank you for listening.